Hey, this is Horner, and this is the Atwoods Machine Lab Notes. Before we begin, we need to take a look and see what's happening in the Atwoods machine. I have two masses. One of them is 105 grams. This one is attached to a rope, which is drawn over some pulleys, and it's attached to mass 2. All the pulleys do is allow you to change the direction of the rope without changing anything else. When I let go of mass number 1, it's going to move in the downward direction. So we're going to say that this is the positive velocity. For this one, it's going to move up. So that is our positive velocity direction. We also know that our acceleration is going to be down on the left side, and it's going to be up on the right side. That means that anything in this direction on the right side is going to be negative. So for example, we know that gravity is going to be negative here. And anything on this side going up is going to be negative. Those are the things that you have to look at first. The motion sensor here will plot a position versus time graph. It also plot a velocity versus time graph. The velocity versus time graph is really what you want to pay attention to. So this is velocity in meters per second, and this is time, and that is in seconds. When you get a straight line for this one, you'll be able to find the slope, and the acceleration is equal to the slope of that line. For the lab, you'll want to read the directions. It'll tell you there's two different things that you're going to do to get some equations and look at some relationships. And the basic gist of this is you're always going to get a velocity versus time graph that you're going to need to find the slope, and then you'll need to record some things. But let's talk about the overall equation that goes with the Atwoods machine, and I'll show you how this works. Let's draw first a free body diagram for each one of these masses. And we will say that our system, or just our object, I guess, is in this big circle here. So we could actually make this a big dot. So this is our great big dot. And we know that pointing straight down for this dot is going to be mg. Because this is mass 1, we're going to call it mass 1 times g. Pointing up on this side is going to be a force of tension. And because we don't have any objects, we just have the string between the two, I know that for this mass number 2, the tension pointing up is also the same as the tension pointing up on this side. Since there's one string here and there's no objects in between, it's not on a table, there's nothing else going on, these two tensions are known to be the same. Pointing straight down, this is going to be m2g. So even though this mass is more massive than this one, the forces of tension between the two are the same. And that's due to Newton's third law. Remember, Newton's third law says that I can only pull on something as hard as it can pull back, or I can only push on something as hard as it pushes back. Because this one doesn't pull as hard as this one does, the tension is actually related to mass 2. And mass 2 can only pull with 100 grams times 10, so that would be 1 Newton of force. This one can pull with 1.05 newtons, but the overall tension is just going to be 1 Newton. So we just know the two tensions are the same, and because of that, we're going to be able to do some really nice math with that. Let's go ahead and do the sum of the forces. So the sum of the forces for our entire system, so that's looking at everything here, is equal to the total mass of the entire system times acceleration. I know that when this accelerates down, this one accelerates up, and these two accelerations are exactly the same. So this acceleration tells me that what the value is here and the value here. So those are both the same. Let's go through and let's do some of the forces. Remember, that's all these forces. So we're going to put all these forces on the left side. So I should have 4 forces here. 1, 2, 3, and 4. We have to be careful because if it's pointing down on this side, it's positive. So we're going to start with m1g, it's positive. ft is negative, so we're going to put minus ft. And then we've got ft on this side, but notice that's positive, so we're going to add ft. And then we're going to subtract m2g, minus m2g. And that's equal to the total mass times A. And the total mass is m1 plus m2. Remember, mass doesn't have a direction, so we're just going to add them. And that's times the acceleration. For these two forces of tension, notice I have ft minus ft, so they cross off. Now I'm left with m1g minus m2g, and that's equal to m1 plus m2 times my acceleration. I can factor out the g, so g times m1 minus m2 is equal to m1 plus m2, and that's times acceleration. At this point, we're going to solve for acceleration. So I'm going to divide both sides by m1 plus m2. And now I am left with the following equation. The acceleration of an Atwoods machine like this is equal to gravity times the acceleration due to gravity times m1 plus m2 divided by m1 plus m2. Oops, sorry. This one's m1 minus m2, so be really careful there. We want to put m1 minus m2 over m1 plus m2. And that is how you find the acceleration of an Atwoods machine.